Hello, welcome to day 2 of vectors. Today's lesson is solely based on applications of vectors. This is 1 through 6 is what we covered in the first day of vectors. So make sure you watch that first or have understanding of regular terminology of vectors before you watch applications here. Here we begin. Before I start the applications, I would like to remind you a few things from geometry. Number one, if we have a parallelogram, then in a parallelogram, all the angles add up to 360 degrees. Number one. Number two, so 360 degrees, all of them. Number two, opposite angles are equal. So this angle will equal that angle, and this angle will equal this angle. Then comes in the fact that vectors, graphically, when you're adding vectors, let's say this is vector v and that's vector w, when I'm trying to add them graphically, we take the first vector the way it is. To that, we're going to add the second vector, and this is the tail of the vector, that's the head of the vector. The second vector comes and sits at the head, so it's tail, head, tail, head. W will come sit right here to be able to add them, and the resultant vectors from the start to the finish. The pink one represents v plus w, or the addition, or the graphical addition of the two vectors. So if I have a vector v in this position, and at the same object, if another force is acting on the same object w, I will have to complete the parallelogram here. I could also consider v acting on this side as long as both the vectors have the same magnitude and same direction. They are equivalent vectors. And w can be represented using this dotted arrow. What that does is, that way I'm able to graphically add two vectors. Let's say this is the starting point. Vector v plus vector w represents this as the resultant vector. So this automatically represents vector v plus vector w. If I go the other way around, so if I go this way, w plus vector v still ends up being start to end position, which still represents w plus v. So we'll have to make that parallelogram and then focus on one of the triangles depending on the situation to be able to add them. And the other thing was to be able to write a vector in IJ format, which we covered in the last class. That vector can be written in IJ format, where I just represents the horizontal component of the vector and J represents the vertical component of a vector. The formula goes the magnitude of the vector times cosine of the angle, stick an I with it for horizontal, plus sine of the same angle, stick a J there for the vertical component. So we're going to be using that formula as well. Let's move on to the first example here. I did do it in class last time, I'll do it again. A ball is thrown with an initial speed of 25 miles per hour, and that tells me magnitude of the velocity is given. Also, they've given me direction it makes is 30 degrees with the positive x-axis. So if that's the ball right there being thrown in the air, the angle it makes with the positive x-axis 30 degrees, and its magnitude is 25 miles per hour. If I were to complete that triangle, there should be a 90-degree angle. Now let's see what the question's asking me. It's saying express the velocity vector v in terms of I and j, which is basically this formula that I just pointed out to, writing a vector in terms of I and j, which can be, they're wanting me to use v for the letter, so that's equivalent to its magnitude times cosine theta I plus sine theta j. Let's plug those values in. Its magnitude is 25, angle is 30 degrees. J, we know the values of these. Cosine 30 is root 3 over 2. Sine 30 is half J, and it's time to distribute. 25 root 3 over 2 I plus 25 over 2 j, and I have written that vector in terms of I and j. The benefit of doing that is now that I know the horizontal component of the vector, which is 25 root 3 over 2, and I also know the vertical component of the vector, which is 25 over 2, which is about 12.5, which means this component of the vector is 25 root 3 over 2, and the vertical component is 25 over 2. Now let's see what else are they asking me. Second, what's the initial speed in the horizontal direction, which is basically this. This is the horizontal speed, and this represents vertical speed. Now just to formally announce it, like how they said, horizontal speed turns out to be miles per hour, which is approximately, I believe, 21.87 miles per hour. That's a horizontal speed. Now the vertical would be 25 over 2, which is exactly 12.5 miles per hour. And that's the foundation of vectors, being able to decompose a vector into its horizontal and vertical component. One more time, horizontal is represented by I, and vertical is represented by J. And I and J would never be replaced with numbers. They're just there to tell us the horizontal and the breakage of the decomposition into horizontal and vertical. All right, moving on to example 2. Here we go. There's a Boeing 737 aircraft, maintains a constant airspeed of 500 miles per hour. So here's the magnitude. Headed due south. Okay, headed due south. And its magnitude is 500 miles per hour. At the same time, there's a jet stream. Think of those as winds. Here's the windy jet streams that are going at 80 miles per hour in the northeasterly direction. So if this is the origin, then we got this one. And we also have jet streams going in northeasterly. That's north, that's east, and exactly in the middle because it says northeasterly, which means exactly in the middle. Magnitude of the winds are 80 miles per hour. So I'm going to use a vector that's smaller than 500. Call that 80. Okay, like I said, if I were to add these two vectors, they're not positioned correctly. You'll have to complete the parallelogram to be able to add them algebraically or graphically. So let's see what they're asking me. They're asking me express the velocity VA of the Boeing. VA is what they want to use for the velocity for the aircraft. I think A is for the aircraft. And then also use VW for the velocity of the wind and express both of them in terms of I and J, which means the same formula that we just used, which was its magnitude, and cosine of the angle, stick an I, plus sine of the angle, stick J with it. So VA would equal 500 cosine. Now the theta is the angle that's made with the positive direction of x-axis. So this angle is the angle made by the aircraft with the positive direction of x-axis, and that's a 270-degree angle, plus sine of 270j. When you start substituting the values, cosine of 270 is 0, so the horizontal component is all gone, and sine of 270 is negative 1, so we have negative 500j as the velocity vector of the aircraft. They want me to do the same thing for the wind. So V of W would be its magnitude, which is 80, times cosine of the angle made by it. That angle is 45-degree angle, like I said. Cosine 45, stick an I, plus 80 sine. I already distributed here, if you notice. Like here I didn't distribute, here I'm starting off by distributing. 45j, so 80 root 2 over 2i, plus 80 root 2 over 2j. 80 over 2 can be simplified, so we have 40 root 2i plus 40 root 2j. And I have expressed the wind factor also, as a vector. So here's the second one. Okay, that takes care of the first part. Let's see, what else do we have here? Okay, part B says find the velocity of the aircraft relative to the ground, which basically automatically means the resultant vector. And when I say resultant vector, that means the velocity of the aircraft and the other force that's acting on it is that of the jet stream. So both the vectors together represent the resultant vector. So V of A plus V of W automatically represents the result of both the forces acting on the aircraft. So find the velocity relative to the ground. Part B here. Relative to the ground automatically means vector addition of both the forces acting on it, which means the first vector is negative 500j. Add to it the other vector, 420i plus 40 root 2j. Adding them, I can only add the x to x and y to y. So these are the two vertical components. Oops. These two are the vertical components. I can add those two, and I can only add horizontal to horizontal. Now, horizontal doesn't have any company, so do I, and then add to j. And this is the resultant vector. I can also call it R, which is the sum of these two vectors, represented in terms of I and j. What that means is the resultant vector, so let me follow the same steps here. Graphically, if this is vector VA, then VW needs to be drawn here so we can actually add them, V of W. And the resultant vector is from start to finish. Let me change color here. Start to finish of this. And this is the resultant vector, the R vector. And that's the actual direction the aircraft is heading under the force of the jet stream. And this vector is represented by the resultant vector. So we know the horizontal component of the resultant vector and the vertical component. Okay, we got done with B. What's C asking us? Find the actual speed and direction of the actual speed, which is indicating towards magnitude, and the direction of 737. Now the direction is basically this angle, and actual speed is the magnitude of this vector, which, like I said, is this vector. So the magnitude of a vector is simply Pythagorean theorem. So magnitude of R, simply Pythagorean theorem applied to its A squared and B values. And it's time to plug this into the calculator to get that magnitude. I didn't do this, so I'll have to plug this in. And then to that, square it. That turns out to be about 443.52 miles per hour. The actual magnitude of them is slower than one depicted here because the jet streams are partially acting against them. So the speed makes sense. Now I also need to figure out this angle. To be able to do that, what I can do is represent the x and the y component of this resultant vector. The x component of this resultant vector, I'm going to redraw it here, is basically 40 root 2. And the y component, we saw that is 40 root 2 minus 500. Now that's angle theta. If I can find this blue angle theta, and then I can subtract it from 90 degrees to be able to get the actual direction angle, because that direction angle needs to be made with the north-south line. So what I can do in this right triangle to be able to find theta, I can set up tangent of theta must equal opposite. This is the opposite side, and that's the adjacent side. Must equal 40 root 2 minus 500, whatever that value is, over the adjacent side, which is 40 root 2. So I basically am trying to find the inverse of 40 root 2 minus 500 over 40 root 2. Tangent inverse, though, you have to make sure you plug in tangent inverse. So theta must equal inverse of all of that. And when you plug this into the calculator, you will get about that angle, which does make sense. It's a negative 82.3 degree angle. So this angle is negative 82.73. And it's showing me negative because we're in the fourth quadrant. So clearly to find the leftover angle, which is what the actual angle is, would be 90 minus 82.7-ish. And that'll give us that theta angle to be approximately 7.27 degrees. That made sense. So this angle would be the 7.2327 angle. And relatively it makes sense compared to the situation. There we go. So that's been taken care of. Moving on to third example, and I think I'll stop the video after third example because it's going to get pretty long. Before I move on with this example, please know that anytime there's an object placed on a ramp of an inclination, here's the object, whatever the object is, let's say it makes an angle of 15 degrees. The weight of the object is always acting towards the center of the gravity. So this blue line represents the force vector weight. Then also, whatever that object is, also exerts force against the ramp. And this one will be perpendicular to the ramp. This would be the force exerted by the object on the ramp, which will be perpendicular to the ramp. And then this one will be perpendicular to the horizontal ground. Okay, one more time. Any object sitting at an inclination exerts two types of forces. One is the force of the weight towards the center of the gravity, which is the blue one. And the other one will be the force exerted against the ramp itself or the surface it's sitting on at. Also notice that whatever this angle of inclination is, this little angle down here will also be equal to the same angle. So if I change this to a 20-degree angle, then, and here's the object, then the force of the weight and push against the ramp surface, this angle will also be 20-degree angle. Just concepts that always apply. Okay, let's see what the question is. Two movers require a magnitude of force 300 pounds to push a piano up a ramp inclined at an angle of 20 degrees. Ramp, 20 degrees. So here's the piano. Okay. And like I said, before I do anything else, we already know that the center of the object will be exerting a force downwards towards the center of the earth, which is automatically the force of the weight. Now they're also saying two movers require a magnitude of force of 300 pounds. So here, this force they have to apply, 300 pounds, to keep it rolling upwards. How much is the weight of the piano? Let me also draw the other force towards the ramp, right there. This will be 90-degree angle. And that force of 300 pounds can be shifted to here to be able to make a diagram out of it. The force is obviously going to be applied to the piano, but relative to the triangle, an equivalent force can be substituted here. This angle will always be a 90-degree angle, and like I said, whatever the angle of inclination is would also be the angle here. Now, the question is asking me just the weight of the piano. So between the two forces, it's asking me to find the force of the weight. And because this is a 90-degree triangle, it's a right triangle, I should be able to apply SOHCAHTOA to it. This is my reference angle, and this side would automatically be the opposite side, and this is the hypotenuse. So opposite and hypotenuse as in picture, which helps me set up the sine formula, because sine is opposite over hypotenuse, so sine of 20 degrees will equal opposite side, which is the same as the 300-pound force, divided by the hypotenuse, which is the weight. I should be able to swap these two without affecting the proportionality. 300 over sine of 20 degrees. Sine of 20 degrees, the force of the weight. And if we divide the two, that's about 877.14. And that is the weight of the piano. And that's all they asked. So that was relatively simpler. All right, I'll stop the video here and then continue with two more examples in the next video. See ya then. Bye.